G'day there. You're watching the Aussie BIM Guru, and today we've got a presentation actually by someone else on my channel. So I'm pleased to announce that Wassim Jabi is actually going to be presenting something using his Dynamo package called Topologic. And he's going to talk to us about how it can be used in order to resolve an issue called closed circuits. So I won't go too deep into what it is. I'll let Wassim actually explain it to you. But previously in the last video that I released, I showed a way you could use Rhino Inside to handle a problem when you convert rooms with common boundaries into curves. You end up with a lot of overlaps between edges between these. Now, Wassim's explored this, but also went one step further to find out how we can find common spaces within essentially an overlap of lines, which is a really relevant problem in many cases that he'll show us. So the problem is that we do end up with a lot of collinear lines that can't be rationalized, and sometimes they don't meet at corners as well. So Wassim's going to show us how Topologic can solve this problem. So Topologic is a company or an organization with Wassim and some other people, and they've essentially been exploring how we can look at the concept of topology to apply to such programs as Dynamo and Grasshopper. And topology is a different way of looking at geometry. It's a very interesting concept. So we will be featuring Wassim today from Cardiff in UK. He's an educator as well, so his presentation style is very interesting. I find him very engaging to listen to. I hope you do as well. But we've been talking about solving these challenges over the past couple of weeks, and we decided to release some content and show a few different approaches. So Topologic, or topology, is essentially a different way of analyzing geometry. So we break down geometry into different sets of classes, which are similar to things you might be familiar with in Dynamo, like points, curves, surfaces, etc. In topology instead, we're always working with a relationship between every single piece of geometry. So even when you create a solid or a cell in this case, it still understands all its components right down to the base class of a vertex. As well as that, we can go beyond just a simple solid or cell. We can build what are called cell complexes or even clusters of geometry comprised of lots of different types of elements. These give a really different way that we can analyze our geometry, which opens up a lot of avenues to look at space analysis and energy analysis. And it's a lot faster and a lot more creative what you can do with this. For example, when I first started using Topologic, I just created this little study to try and find the shortest path between a cluster of cells in 3D, which is really relevant when you're looking at something like fire egress, for example. But in this case, he's going to initially be talking about how he deals with identifying what closed shapes exist within a network of curves, which is quite a common problem. He's going to show us in the context of a roadmap first, which is really handy for urban and civil planning, and then he'll move on to look at a building similar to my example. There are going to be some resources that you can reference from his website, in this case the topologic.app website, where there's a lot of scripts you can download, and also the topologic package itself. And there's a couple of new nodes that have come out of the work that Wassim's done with me, so I really look forward to seeing what you can do with it as well. Anyway, I'm going to hand it over to Wassim, and I hope you enjoy his presentation.
Hi everyone, my name is Wassim Jabi, and as Gavin Crump, the Aussie BIM Guru, probably told you, we've been discussing over Twitter and LinkedIn ways to get data from Revit and create closed polygons or closed circuits and that are touching, that the edges between them are actually touching, so that you can create adjacencies and you can build three-dimensional cell complexes and do energy analysis, which is what Topologic can do very well. So he has probably shown you already the process he went through with Rhino Inside, and I thought I'll show you an alternative approach, or maybe something that complements what he has done, because I took the file that he sent me, the resulting drawing, and I was able to build a topologic cell complex out of it. So I've been thinking about this, and I did a few experiments, and I ended up creating two Dynamo custom nodes that are now on the website, so you can go ahead and download them and test them for yourself. And I hope these two processes and these two approaches would really be helpful for you. So let me tell you what the problem is. The problem is that many drawings that you come in, if you're dealing with Revit, you are creating really well-structured data in most cases. But many of you are still working with just sketching programs, AutoCAD, excuse me, and you have just lines. And the question is, how do you clean up those lines and create meaningful circuits and polygons so that you can build three-dimensional entities out of them? It is not a new problem. When I was at the University of Michigan doing my PhD, the researchers there, Ted Hall, Jim Turner, Harold Borken, they were working on these algorithms 35, 40 years ago. So these are not new algorithms, but it's good that we bring them back and put them in Dynamo. So the problem, as you see here on the screen, is that you might have lines that are extending, they are not intersected. So what you want to do are two things. You want to trim the loose edges that you see here, what I call non-manifold edges, and so you create like a clean boundary kind of representation, and then derive the closed circuits from that boundary. So the short answer to the solution is that you have to do two things. First, you have to work kind of like from the outside in, from the loose edges, from the vertices that have only one edge connected to them, and work your way in until you find a vertex that has more than one edge connected to it, and you stop there. And it just works itself out. You can look at the Python script for more details of how it works. Obviously, there's a little bit more to it. So that's the first one, is to kind of like trim those lines. The second one is what I call go left or go right if you want. It doesn't matter which direction, but you take the most extreme. So reaching an intersection, you take the leftmost road, let's say, the path, or to your left. So if you are in the UK and you reach a kind of a roundabout, you take the first exit, basically, to your left. And when you do that, you hope to get back to the original vertex. Now, this works in, I would say, 99% of the cases, but you will see at the end of the video, there are some cases where it will still work, but it will create a non-manifold condition, which you will have to be aware of. But I'll discuss that a bit later. But here is the first example, very simple. You try it on a very simple geometry just to make sure it works. So you'll see this shape on the left has some kind of extending lines, intersecting lines, and the script will clean them up and give you, actually, in what you see on the right is actually made out of three circuits. The two rectangles as well as the square that is the external boundary. And the script will give you all these separately so that you can deal with them separately. In this one, I used a plugin for Dynamo called Dynamaps, which is really interesting. You should try it out, which brings in street networks and building footprints from OpenStreetMap. And what I did is I cleaned it up. You can see here the two nodes, the two custom nodes that I created, both clean it up and create circuits. So I'll show you the circuits next. So I made faces out of these circuits, and then I offset them in the Z with a random value a little bit just to perturb them so that you can see the different pieces. So let's go live a little bit, show you how these things work. So I will start with Revit because it's the simplest way to get to this data. So if you look at the sample architectural project that they have, the advanced one actually, they've done their job. They have actually all the rooms and all of that. So let's see how we can convert this into Topologic. So I'll just go through the nodes a little bit. Sorry, they're not very cleaned up, annotated, etc. I'll try to do that and then put that on the website as well so that you can use not just the custom nodes but the actual workflow. So very quickly, most of you know this stuff, getting the rooms categories, getting all the elements that are rooms. So these are all rooms, 91 rooms here. Then I get all the levels and I choose the entry level, 01 entry level, convert it into a string. So now it's called 01 entry level. I get from all these 91 rooms their own level. So I'm getting that parameter name, which gives me, some are 01 entry level, as you can see here. Some are 02 floor, 03 floor, etc. So I filter by the ones that are 01 entry level, so I test whether they are equal to this string, and then I do a list by filter by Boolean mask, as you all probably know. So now I'm getting only the rooms that are on the first level. And these are the rooms. Now I have 31 rooms. Great. So now it's very easy actually, because you have something in Dynamo that's called room.center-boundary. And honestly, I did not know about that one before. So that when I discovered that one, it was really fantastic, because this one gives you the center lines of the walls and cleans it up so that it intersects correctly. So you get something that is very much ready for Topologic to actually build adjacencies. So this gives you a drawing that is very similar to testfit.io. So if you know about testfit and how it works and kind of the data, and I've tweeted about it and I have put on the website some workflows that take testfit data and build three-dimensional entities, and you can do energy analysis. I've shown how you can do energy analysis on them, and you can do exactly the same here, because if you look at these boundaries, and apologies if it's not very clear because it's below the faces because I offset them, they are single lines and they are all kind of cleanly trimmed against each other, and rooms share these lines. So once you have this kind of shared edge between a room and another room, you can do adjacencies, you can do topology, you can do energy analysis. Now you notice we have these columns as well, so these came in as well, so we need to perhaps clean them up a bit later, but we'll deal with that. So basically once we have these room center boundaries, which are these curves, we can create topologies from them. This is now Topologic here. So topology by geometry is the entrance into Topologic. So now we have a lot of edges, and they're still organized by their rooms. So 4 edges or 5 edges to a room. The ones that are 2 edges are probably the columns, because they're 2 arcs, semicircles, forming a column, a circular footprint. And then we call wire by edges. So now we have all these wires. So think of a wire as a polycurve or a polygon. So it's basically a group of lines. In Topologic, a wire doesn't have to be closed. It can be branching. It can be non-manifold, and I'll show you the effect of that a bit later. So thankfully, all these wires are closed. So because they are closed, I can build faces out of them. So this is again a Topologic face. So face by wire creates all these faces, and that's it really. I have my topology edges here, and I kind of build them all up. From here, with these faces, I can, for example, offset them by 3 meters, let's say, and create a cell out of them, and then I can build a cell complex out of these cells, and that can be then energy analyzed. So I'll show you the kind of the effect of doing that. I haven't done it in this workflow, but this is kind of what I have done with testfit, so it's exactly the same process. These entities that you see here on the screen all started by being faces or wires, 2-dimensional wires that have been extruded up. But the trick is that they need to be absolutely kind of clean in terms of how they are touching and the edges that they share. So that's fine. You say, oh, that's simple. That's very simple. The most difficult thing was finding room.center boundaries. But what if you are not dealing with Revit? What if you are dealing with AutoCAD or some other sketching program, and your data is not well structured, like here in rooms? You just have a bunch of lines. How do you actually get to this point from AutoCAD? So let me show you a sample drawing that I found online, and I cleaned up a little bit. So this is AutoCAD, and these are what we call dumb lines. They're just lines. There's nothing more to them. This is a kind of a typical floor plan that you see. I did some things to it to clean it up and make it ready. So let me go over those and tell you what I have done. First thing I have done is I replaced all the door swings and the pocket doors with just simple blue lines. And anybody who uses AutoCAD, I haven't used it in many years, it should be an easy task to kind of replace all doors with just the single line for the width of the door. The reason for doing that is that if you leave the door swings, the arc of the door will be part of the shape of the room, and actually the inside the door will be another room, another closed circuit. So you really don't want that, as well as the door leaf as well will be a different circuit. So you should just simply abstract it a little bit and just put a boundary between rooms as a single blue line, as you see here. The other thing I did is I found some overlapping lines, and this drawing was not clean. So you find like these edges that are look like as if they're one edge, but they are made out of multiple edges on top of each other. Topologic should be able to handle this, and it handles it in most cases, but sometimes just because of tolerances and floating point, decimal points, etc., sometimes it can miss some of those. So just not to get into trouble with that, I went ahead and cleaned all of that. The last thing I did, which was just for convenience, is some of these pillars, I call them, I guess, like what you see here, this one here, had an actual rectangle inside of it, so it was hollow on the inside. And that would have created another circuit and another wire, like independent from the other ones. So I just wanted the wires that I'm interested in, like as if I'm gonna laser cut this. I didn't want the hollow piece in here, so I deleted these rectangles from this pillar, this pillar, this pillar, and I think there was another one over here somewhere. Yeah, this one here, right there. Okay, now the third thing I did was this drawing had a lot of furniture, bathtubs, toilets, etc., kitchen sinks. So I removed all of that. I deleted those layers. We don't need them for this kind of work. But on purpose, I left some lines that are non-manifold, that are kind of like loose edges sticking out, and I put them on a layer by themselves called mistakes, and they're indicated here in red. So things like this, I just wanted to test that my script can actually clean that up and remove it from the drawing, as we saw before in the presentation. So you see these red lines, and here as well. They were part of the drawing, and I just left some fragments of them just to test and see what happens. Okay, so how do we get this into Dynamo and Topologic? Now, if you are dealing with Dynamo for Revit, that should be easy. You can bring this DWG into Revit and then maybe convert it and move it over. But I don't use these types of processes. I use Dynamo Sandbox all the time. So I wanted to get it into Dynamo Sandbox, and I'm trying to think like what workflow should I, what file format should I use? Luckily, there is a piece of software that I use on the side. I keep it, for like experiments and for Python scripting, and it's based on the same engine called Open Cascade as Topologic. And this piece of software is called FreeCAD. Maybe some of you know about it. It's a fantastic piece of software. It's not for the faint of heart. It's an open source FreeCAD, as the name implies. But it is based on Open Cascade, which means that it can save to the same file format as Topologic, which is called BREP, boundary representation. But the good thing about it is that it can load or import DXF files and DWG files, etc. A lot of files actually that it can import and export, and it's all for free. So I loaded this drawing into FreeCAD, so I'll show you that. There it is. And the nice thing about it is that when you select all the faces, it highlights the vertices. So that's where I discovered that there are overlapping edges, and this is where I cleaned it all up. So now this is a very clean drawing, as you would expect. And then I go ahead and export, and I use the BREP format, and I called it an AEC plan. Okay, so now that we have BREP, we can go to Dynamo and Topologic, and we can import that BREP. So I'm going to go ahead and show you the workflow for this. So let's start from here. We open up the BREP, we import it. This is Topology by imported BREP, and what we get here is a cluster. It's just a cluster of edges, like a group of edges. So, but then we self-merge this. So now that we have self-merged it, we still get, oh well, in this case we got a wire. Sometimes you get a cluster. So in this case, it kind of cleaned it all up and gave us a wire, which is fantastic. So we're kind of ready to go. And this wire has 939 edges, 855 vertices. So you can use topology.analyze to figure it out. So now this one is not needed in this case, that's why it's not connected. So I'm going to go ahead and delete those. Because if it was a cluster, you would get the wires out of the cluster, and then you would get the first wire, like here, W0, and then you have a wire and you can deal with that. If it had, let's say, other pieces, if it was not all contained. If it is all contained, you just have a wire and you can just simply start with the wire immediately. So let's go ahead and delete those. And this is the actual custom node that is on the website. It's called Wire Closed Circuits. And what does it do? It basically does two things built in. It takes the wire and removes all the loose edges and then tries to find circuits inside. Now, when you're trying to find circuits inside the wire, some of these circuits are clean, like polygons, but some of them can kind of trace back onto themselves, like they can go into a little island in the middle and then come back out. So you can imagine like almost like a C shape, but that is closed with an internal circuit. I tried my best to kind of clean those up. It didn't work, so I decided I'm just going to accept them and leave them as what I call non-manifold circuits. So I put them in two different sets. If it's a clean closed wire, I put it in a list called manifold circuit, and if it is have that kind of non-manifold characteristic, I put it in a different list. And in addition to all of that, the algorithm finds the external boundary. So you just trace the outside of the whole drawing, and I put that in a wire separately called external boundary. So you can get to deal with that if you need to. And that's really it for now. For this one, there are no non-manifold circuits, but you'll see in the second workflow there will be some. So I create a face by wire. I draw them as well, and then I randomly offset them up in the Z so that you can see them. So this is what this is all about here, and I draw the edges. So let me show you the drawing of it. So here it is, and everything is in there. So this would be really very good for moving this forward, extruding it up, or even laser cutting it, because these are all separate pieces now. So you can even build a model out of it. And what you see at the bottom is the actual raw data, the actual wires that came in. So this is from AutoCAD all the way to something that you can build three-dimensional entities out of, and build also topologies, so like adjacency information will be now easy to obtain. So this is if you are working in an AEC workflow, but if you are working in an urban design type of workflow, let me show you that. So this one, as I said, I used Dynamaps, which is really great. You can choose any location in the world. If there are roads and building footprints, you can bring them in. You can decide how to bring them in. But let me show you what this data came in as. So this is the original data, like this. And you'll see there are all these extra lines, etc., that needed to be cleaned up. So you bring it in topology by geometry. Now we have 304 wires, because some of them are closed circuits. We get the edges, so we just need raw edges here. So 940 edges. We flatten the list, so 940 edges here. We create a cluster by topologies like we did before. So now we have a cluster of edges, but that doesn't have any topological connections yet. It has not intersected them. And we simply call topology.self-merge. So topology.self-merge is really very useful. Cluster by topologies and then topology by self-merge. These two nodes together are very, very useful for lines, because it will intersect all of them and create the highest possible topology it can, like a wire out of it. Or if it is a three-dimensional, it will create cells or cell complexes. So self-merge will try its best to build the best representation of your data. So in this case, it built a cluster again, because there are some islands and kind of separate pieces. So it cannot be a wire if it has disjointed pieces. But this cluster has wires in it. So if you look at the analyze string here, you'll notice that it has two wires. See, right there. So we need to find out what these two wires are. So we get topology.wires out of the cluster, which gives us the wires here. And we take a look and we discover that actually wire 0 is the correct wire and wire 1 is some kind of line fragment, little line fragment that's errant somewhere, just on its own. So we kind of ignore it. So we take a look at this wire 0 and we again pass it to wire.closed circuits. And in this case now, it gave us manifold circuits, which are closed. These are the dark gray ones. And we are able to build a face by it and convert it to Dynamo geometry here. So 149 faces worked well, but we have, if we do a watch panel and we look at the non-manifold circuits, we got 4 non-manifold wires. So let me tell you where they are and what they are. Basically, they are those ones that are highlighted in blue. And what you'll notice, what they have in common, is that, as I said before, they go in and they create like an island in the middle, and then they go out again and continue tracing the whole polygon. So it's a valid wire, but it's not a valid face. And Topologic cannot build a face with a hole in that kind of condition. It can build a face with a hole if you give it external boundaries and internal boundaries that are not connected, they're not touching each other. You just simply give it kind of overlapping boundaries and it will build a face with a hole in it, or multiple holes. But you'll notice all of them have the same characteristic. Now I might in the future look at the script, or maybe you guys, if you know programming, can help me out and clue me in on what I did wrong in order to solve this problem. But I got the internal islands, that's absolutely fine. I got rid of the non-manifold edges, but these types of edges that are not considered non-manifold, they can be traced correctly and they are part of the topology of it, but I cannot build faces out of them. So I just leave them as is. We have the wire, but then I cannot build faces. That's it, really. As I said, I hope you find these useful. I want to give my thanks to Kevin, who really kind of discussed this with me, guided me through some of the issues, and I hope you can benefit from both our approaches to it, because they probably are also complementary. And if you have any questions, please contact me, info@topologic.app. And if you're interested in these two custom nodes, you can download them from the website, again, topologic.app, under the learning section. Thank you again for watching.
So that concludes the first part of Wassim's presentation. I hope you've enjoyed it. I definitely did, and I learned a lot about Topologic as well. I've been using the package a little bit in the past, and it's great to see just how someone with the mind geared towards Topologic really uses it, because I mean, Wassim clearly thinks in this manner, so it's a really interesting way to see someone work. And I'd like to thank Wassim personally for actually contributing his videos and his content to place on the channel. And I hope that this sort of further shares his workings and his ideas, and it encourages some of you to try out the Topologic package, and also just think about what you might be able to do with topology instead of geometry, because there's a lot of applications that we can use it for. So I look forward to sharing some of these in the channel in future as well. So thanks for watching today. There will be a second part with Wassim, where he goes back and actually looks at the specific example that I looked at as well, and shows you how you can take this a few steps further to form some meaningful analysis sets to work with. So I make 2 videos every week typically, so if you're not already following and subscribing, feel free to, and don't forget you can go over to topologic.app and check out what they're doing at Topologic BIM as well, and I'll see you in the next video. Thanks, take care, bye.